So, welcome back student to the next class of complex analysis. In the previous class we learned few things about the Cauchy-Riemann equation and analytic function, and if a function is given to you, the Cauchy-Riemann equation suggests that ux is equal to vy and uy is equal to minus vx, and if they satisfy this relationship, then the given function fz is analytic in nature. Now, today I like to show another angle of another way to derive these things regarding the fact that for analyticity the derivative is important, because the analyticity of the function means that its function should have some derivative at particular point, not only that, in the neighborhood of that. So, when we do the derivative, if you remember, f prime z is defined as f z plus delta z minus f of z divided by delta z, limit delta z tends to 0. With this limit, I can write the expression of this. During the calculation of this Cauchy-Riemann equation, we approached this condition in two ways. One is delta f was delta u plus I delta v, and delta z was delta x plus I delta y. And then I mentioned that when delta z tends to 0, and you can do this delta z tend to 0 in infinite way, because it can comes from anywhere, but I choose to prefer direction. In one case my delta x was tends to 0 and my delta y was 0. So, that means if this is the point I am approaching from here to here and here to here, making delta y equal to 0, that was my one approach. And in the second case, when I put delta tends to 0, the second case, our approach was something like this, that delta y tends to 0, but delta x is equal to 0. That means I am not approaching this side because I put from the very beginning that delta x is equal to 0, and I am approaching this side so that this limit can satisfy. In order to satisfy this limit, I take two preferred condition and this, and when I do that, then I derive this equation. But the question is this equation really, is this way really gives you the total picture? Because I ignore all the other side approach, I take to preferred direction and then the calculation is done, and from that I am getting this expression in my hand. So, today I like to show that this equation is essentially gives you the fact that even though I am getting this expression by using these two preferred directions approach towards this 0 point delta z equal to 0, it essentially the fact that if I do the same thing, these two expression is basically gives you the same result in all the approach in any direction. Try to show that in a different way. Okay. So, I do hope you realize exactly what I am trying to do. Cauchy-Riemann equation is derived for two preferred direction. Now, I am saying that the Cauchy-Riemann equation is something which is sufficient to show that if this two equation is satisfied, even though I am deriving from two preferred direction, it is the same equation that you will get if you will approach whatever the direction you want. So, let me do the thing here in this way. So, this is the point I have z, and another point, this point is z plus delta z, this angle is alpha. So, from this, so here in the complex plane I have one point z. If I want to approach this point, then if I change this point to some direction within making an alpha, so this is my delta z, which is the small increment of this point. So, delta z can be represented as, if I write this radius is epsilon. So, epsilon e to the power of I alpha. Delta z I can write always, because this is the point and I want to put another point delta z which radius is this epsilon, and if the alpha is given I can write it. So, that means this quantity is epsilon cos alpha plus I epsilon sin alpha, which is delta x plus I delta y. So, delta x is epsilon cos alpha, delta y is epsilon sin alpha, that I have, these things I have. Okay. Now, what I do, delta f is delta u plus I delta v. U v are function of x y. So, delta u I can write it as u x delta x plus u y delta y plus I delta I v x delta x plus v y delta y. I just expand delta f, which is the small change d delta u and small change delta v. Delta u and delta v are function of x y. I believe all of you are aware of these things. If u is a function of x and y, then du can be represented as del u del x dx plus del u del y dy. I am using this simple thing here. When del u del x is u x, is the partial derivative with respect to x, partial derivative with respect to y, and the increment. Okay. Now, if I write these things, this delta x and delta y, so let me write it first. Let me write this expression in this way. I just slightly rearrange this equation. Whatever the equation I have, I am just slightly rearranging that. There is a, I mean, even though I am rearranging that, but you should note one thing carefully, that during the rearrangement I take u x and v y which are related to Cauchy-Riemann equation, u y and v x which is also related to Cauchy-Riemann equation, and I will separate out these two with this form. Now, I like to put this delta y value, delta x and delta y value that we have here. So, it is u x, epsilon is both the cases we have epsilon. So, I can take epsilon outside, u x delta x is cos alpha plus I v y sin alpha. This is my first expression. Second expression is again I can take epsilon outside and uy is here. Delta y is how much? Sin alpha plus I v of x cos alpha. This. Now, what I will do, I will again rearrange these things slightly. So, epsilon ux cos alpha plus I vy sin alpha plus I epsilon, I take I common from here, Vx cos alpha minus uy sin alpha with one I inside here. I am taking I common from this side. So, I will be here, there will be no I with this term Vx cos alpha. So, Vx cos alpha is here, uy sin alpha. So, I take one I outside. So, minus I should be here. So, uy sin alpha, it is something like that. So, this quantity is my delta f. Now, let me erase this thing, I do not have the space in the board to go down. So, what is my limit? What is my derivative of this quantity? So, limit delta z tends to 0, delta f by delta z. Delta f I figure out, delta z is also giving here. So, if I write this expression should be something like this, epsilon ux cos alpha plus I vy sin alpha 1 plus I epsilon. Let me erase this part, it is not required. I alpha, then Vx cos alpha minus I uy sin alpha whole divided by epsilon e to the power of I alpha. Now, the limit is delta z tends to 0. Delta z tends to 0 limit is essentially the limit epsilon tends to 0, because if you remember the figure, it was something like this. This was the point, this was the alpha, this was the epsilon, this z, z plus delta z. So, now delta z tends to 0 means this length I can come to this point with this direction. Alpha is the direction, the preferred direction, and I am coming to this point by making epsilon tends to 0. That means, this length can squeeze to this point. Okay. Now, you should note a very interesting thing here, and that is the reason I derived these things to show. So, now epsilon tends to 0. So, I can cut this epsilon, and this entire quantity now depend on one variable which is alpha, Now, if I say that whatever the approach may be, in which direction I go to that particular point, if it is alpha independent, that means my derivative is true for all approach, not any preferred direction. So, that means, let me try to understand once again. This was the case, this is epsilon, this is alpha, this is z plus delta z. I try to make this delta z 0, and my approach is now depend on alpha here. So, downstairs we have 1 alpha and upstairs we have 1 alpha. is it possible to make this expression alpha independent? If the expression is alpha independent, I shouldn't bother that what is the angle of this alpha. I can go from here, I can go from here, I can go from here. This alpha is not a very important factor here, if I make this expression alpha independent. Now, is it really possible to make these things alpha independent? In fact, if you look very carefully, when I put this ux is equal to vy and uy is equal to minus vx, we will suddenly have something special here. So, what I am having vy I will replace with ux. So, I will have ux e to the power of I alpha cos alpha plus I sin alpha, I will have this plus I alpha alpha, and this alpha has already gone. So, alpha. So, now what I will do, I will replace this vy, I will replace this vx to minus of uy. So, if I do that minus of uy, so it will be something, let me check once again. So, I replace ux here, and now I will going to replace, it is I am going to replace uy as uy as minus vx. So, just I replace uy as minus vx. If I do, then I will have vx uy, I just replace minus vx. So, this term will be plus. So, eventually I will have e to the power of I alpha divided by this quantity is already there, e to the power I alpha. So, result is ux plus I vy vx, this quantity which is alpha independent. So, when this quantity is alpha independent, when I put the Cauchy-Riemann equation and plug it to this expression. So, Cauchy-Riemann equation, when I plug this to the original expression, gives me the fact that my f prime z is alpha independent. That means, whatever the approach I go to that particular point, this is I mean it is independent of this alpha. That means, every time it is, if I go to whatever the direction I want. So, Cauchy-Riemann equation gives you the fact that it is true only when the Cauchy-Riemann equation is satisfied. That means, it is a cross verification that Cauchy-Riemann equation is sufficient to gives you the fact that the given function is whether analytic or not, and the derivative is exist or not. The derivative is exist meant the limit should be exist in that case, and the limit should be approached from all possible directions, and here I find that the direction is independent, the result is direction independent when I put the Cauchy-Riemann equation in the expression. So, this proves that Cauchy-Riemann equation is sufficient. This is another way to cross verify that how Cauchy-Riemann equation is important and it is sufficient at that point to find out whether the function is analytic or not. Okay, the next important thing I would like to put it here, that what should be the polar form that I mentioned in the last class for the Cauchy-Riemann equation. So, the polar form is something which is important also, because the function z can be represented in r e to the power I theta, this form which is polar. So, now r e to the power I theta can also be represented as r cos theta plus I r sin theta, and if I write this now u plus I v, then my u will be function of r and theta, and v is my function of r and theta as well. Since u and v are now function of r and theta, so it is important to know what should be the relationship between the r theta in polar form, so that I will have a, I mean ux is equal to vy, this is the Cartesian form of the CR equation, but I need to find out the polar form. Okay, so let us do it with this. So x is r cos theta and y is r sin theta. That we know. This is the starting point, because we know that a particular point z, when it is represented in terms of x plus I y and is represented r e to the power I theta, these are the relationships just before I derive it. So, now u is a function of x and y. So, if I write du, it will be ux dx plus uy dy. So, now from this equation I can write what is my u theta, partial derivative with respect to theta. It should be ux dx d theta plus uy dy d theta. From here, if I do dx d theta is r minus r sin theta and dy d theta is r cos theta. This is one expression, because this relationship is required here, and other expression also I required. I will do that, but let me finish it first. So, it is ux, this quantity I will put, which is minus of r sin theta plus uy r cos of theta. U theta is this. So, it is say minus of say r, if I write it uy cos theta minus ux sin theta. Okay, I will have one expression in my hand, it is something like this. In a similar way, exactly in the similar way, I can have ur. Ur is ux dx dr plus uy dy dr. Ux dx dr is from there I can readily write it is a cos theta, and uy dy dr is sin theta. So, two expression u theta and ur I find. So, I should write it somewhere, because I need to use this again. So, u theta is r u cos theta uy cos theta minus ux sin theta, and ur is ux cos theta plus uy sin theta. Okay, I will do the same thing for now v. So, if I do, then I will have two relation and then compare, then it is done. So, in a similar way, if I write v theta, which is ux, then sorry, it is vx, then dx d theta. So, minus of r sin of theta plus V y r cos of theta. So, it is say r V y cos of theta minus V x sin of theta. What about V r? V r is V x into del x del r. So, I am doing the same thing. So, that is why I am not writing explicitly. I believe all of you will get, because the same way I calculate this u, I am doing the same thing for V. Expression is same, and then u r dr d thing, that means it is sin theta. Okay. Now is the time to compare these two things, and then we will be getting something. So, let us start with this. If I, so it is u x u y. So, here. So, now if I compare this and this and this and this, I will get something. Okay, let me first compare these and this. If I write this equation r u r, it will, in the right hand side it will be r u x cos theta plus u y sin theta. Now, if you look this equation V theta, and now V theta, if I write it here V theta r V y is V x, u x is V y. So, V y is u x. So, u x cos theta and V y is minus of V x. So, plus V u y is minus of V x. I am using the Cauchy-Riemann equation right now. So, replacing V y and V x in terms of u x and u y, if I do that, then I will find both the things are same. These things and these things are same. Mind it, this is V theta. I just replace this quantity and this quantity, this and this quantity, by using here to here and here to here by the Cauchy-Riemann equation. So, these two things are same. So, when these two things are same, I can write the expression between. So, this is one expression we have, and the expression is r of u r is equal to V theta. This is the polar form of Cauchy-Riemann equation, one equation. And next I will compare the other one, and the other one is this and this. So, again if I multiply this with r, so r V r is r, I will change this V to u. So, V x is minus of u y cos theta and V y is u x of sin theta. If I do that, this quantity is here u y cos theta and u x with a negative sign. So, I can write it like minus of r u y cos theta minus u x sin theta. This quantity from here I can write minus of u theta. So, my second expression is r V r is minus of u theta. So, these are the two expressions that we have. This is the same expression, Cauchy-Riemann equation. This is the same expression or the same relationship that we have in polar Cartesian coordinate. So, this equation now in polar coordinates. So, this is the polar form of Cauchy-Riemann equation. So, polar form is Cauchy-Riemann equation is this, and Cartesian form that we already know. So, here I would like to stop, because after that we will go to the next topic. So, before going to finish, let me quickly do one easy thing, so that you will understand the consequence of this equation. So, let me try whether I can finish within the time frame. So, this is my equation, Cauchy-Riemann equation. Now, a function is given f z is z. I know this z is analytic function. Z is r e to the power I theta. So, what is my u here? U is r cos theta, and my v is r sin theta. Now, if u and v are given, are they satisfying this equation? Because this is analytic equation, analytic function. So, it should be this satisfying these things. So, let us do that. U r is how much? Cos theta. U r is cos theta, and u theta is, okay, let me, r u r is how much? R u r is r cos theta. What is v theta? V theta is r cos theta. So, this is v theta. So, first equation they satisfy quickly. First equation, so r u r is v theta, they are satisfying from. So, z the most simple function I am taking, because it is an analytic function. If it is an analytic function, whether they are satisfying this Cauchy-Riemann equation in polar form or not, I am taking this as a polar form. So, first thing I check. What about the second one? R V R is minus theta or not? So, R V R. So, V R is sin theta. R V R is r sin theta. And what is your u theta? U theta is the derivative of this. So, r with a negative sign minus sin theta. So, these two are again same. So, the relationship r V r is minus u theta is satisfied here. So, you can readily check that when a analytic form is, when a analytic function is given in the polar form, this is the way you can readily identify whether the given function which is given in the polar form is really analytic in nature or not. So, with that I would like to stop here. In the next class we will start a very interesting thing and very important thing, which is the integration, the line integration and all these things. The concept of complex integration will come gradually come with this concept. So, next class onward we will go to the concept of this, as I mentioned, integration and all these things, and also we will like to know something about the singularity, what is the meaning of singularity and all these things. So, with that I would like to stop here. Thanks for your attention.